Well, I'm Charles Poe, manager of discrete computation at Wolfram Research, and I'll be talking about the new advance in geometry computations. The talk will be essentially what we have been doing for the last release version 12 and all the new features coming from the upcoming release. Well, I'm Charles Poe. Working with the discrete computation. And I'm going to talk about the advance in geometry. Well, essentially what we have been doing for the last, what we did for version 12 and what we have been working since version 12 for the next release later on. And mainly I will focus more to give you kind of an idea where we are going, the direction, as well as trying to answer several of questions, several of you have been asking during the conference, and how we hope to improve geometry, not graph, geometry step. Okay. Well, the key idea in general is that we build constructor, we have operations on those constructor, and we have solver. Since the release of geometry is essentially what we do. Constructor is like a disk, operation is area on the disk, solver is, for example, you take the disk, you put it in integrate, you get the result. So that's roughly the general idea how we build the whole framework in graph and we integrate it in the system. So in version 12, what essentially we did is that we enhanced the set of constructor. Well, we didn't worry first about the solver, so we enhanced the constructor. We added more operation. Currently, the solver are in the same state as before, but we hope to add support for the new constructor to those solvers. So what I mean is, for example, if you add a new constructor like Polyhedra, we actually need to support it in integrate or in solve or in an integrate and such, right? The same as optimization or visualizations. Right? And the first release actually of geometry, we try to propagate, those constructors in the whole system, right? So if you take image, we use geometry there. You take visualization, we use geometry. You do symbolic computation. You can actually use a region. Because we believe that region is kind of one of those first-class citizen objects you need to, which is essential in the language when you want to express things. Right? We actually live in 3D, right? So if you want to describe something, usually you have to actually represent the geometry. So we focus on constructor operation and usability. So it's kind of one point where we want to improve the usability of the system, make stuff work smoothly. You don't have to convert something to a mesh region and such. So we try to improve that usability so that it just works. So one first thing we introduce, which is a constructor, but as well as is in that direction of usability, is the region wrapper. Right. So one thing is that with region wrapper, the region wrapper essentially auto-visualize anything you have. So it's kind of a representation of a geometric object, independent on the underlying structure, right? So if you take a mesh, you put it in region, it will visualize, it doesn't really think about the cell description behind the mesh structure, the same as a disk or anything else. So that's kind of roughly the idea. So if you think about it, it's really that subset of Rn idea, right? You don't look at the description behind the scene. And that object, obviously, you can take it, compute the surface area, or you can look at it as a just a visual object. You can apply plot team. We have really nice plot team, and then you can get, nice look of those. So what we think about region is that key object. You can just wrap, you generate a region, you wrap it around, you use region, you wrap it around, you get something visual. And then you can still continue to do computation with that. And later on, I will start it explain the distinction between that and mesh region, because there will be a key difference. Instead of even wait later. So essentially, when you have a mesh region, you decide to do Boolean operation. For example, you do difference of two mesh regions, right? So a difference is an open, when you remove an object for another one, you end up with an open set, right? But when you manipulate mesh, you want to, get again a mesh. So mathematically, it's not correct. Right. So in mesh, we will preserve that property people want. So we return you a mesh. So that means we add that additional object. Essentially, we take the closure of the set. But region will not do that. So region is purely that set point in Rn. So if you apply the same operation with region, you will get a formal expression which represents you that open set. So it's where you start to see that distinction. So we kind of provide you both worlds, right? The pure mathematical one as well as the one of modeling of manipulation of mesh. So that's roughly the idea why we have region and the constructors. Well, we added additional constructor for mesh. So we added the fractal set, counter set and such, as well as the different space filling curves. So you can just type them, use them in dimension 2 or 3. And what also we did is essentially we improved the discretization, and that's a continuous work in that side. So you can take an object like that and discretize it. I think this is just the plot range we need to fix. And actually get the object and do computation on it. Or convert it as a region. Which, by the way, in the latest release, you can take a mesh region and just feed it inside graphics. It works. Virtually like a primitive, a graphic primitive. So it's more for convenience, right? When we don't want you to apply show on it and change it. So it's that whole idea of usability. We try to make stuff just work. Okay. Well, one of the key components in the whole geometry are Boolean operation. So we are continuously working on it. We do our best to improve it every time, right? So Boolean operation in any dimension, but currently we focus essentially in dimension 2 and 3. So here we kind of show you with the new primitive, you can do essentially union. And as you see here, I'm using the wrapper region just to automatically visualize it in case where it comes back unevaluated. There we have a nice slice of your object. And behind the scene, we roughly use BSB3 to do that. So we render you the object, roughly kind of a volumetric object. And here you have the difference. As I told you before, it has a mesh region. And in this case, it was a polyhedron. So we assume that they are closed. So that's why you actually have that piece. But if it's, you are purely doing mathematics, you should normally don't have that set on that boundary. And the same for region difference. So you have actually the hole inside, then the object is closed. So in this case, you actually apply opacity, which is kind of, you can actually use wrapper inside the region to actually manipulate your object. So it's kind of all that usability we try to provide, so you can just easily manipulate things similar to what you have in graphics, but you're still playing with the geometry. Well, several of you have already seen this. We showed in the last conference. We we provided in a mesh assistant. So you have actually an additional cell there below where you can actually just click on it and you have a view of property of your mesh. You can also modify it. Here we have the list of the plot teams. Let me take a sample one, that one. So automatically we change it in place. So it kind of allows you to easily just take your mesh and I will say roughly edit it. So you apply all the basic operation we have. So you have the plot team there, you have decorations, and you have the different viewpoint to actually change for your object. And we hope in the future, to add more operation there, so it's kind of more convenient for manipulations. And the last thing I will probably talk about coming from version 12, no, actually I will add a little bit more, but coming from version 12 in terms of usability is the summary box for polygons. So usually before when you were, entering a polygon, you evaluate, it gives you the unevaluated form of polygon. So in the new form, we have a summary box, which you have a polygon, a little view of the polygon, and if you open it, we actually compute some property. It's kind of a delay evaluation. It will tell you it's a polygon with holes. These are the bounding box and probably the area. And it's actually quite convenient because, like in this case, I generate, just 6 polygons. Actually, it should be 60. But so you see that it typeset nicely. You can actually play nicely with it compared to just returning a set of unevaluated expression. right? So it's part of that usability. We try to make the whole system more convenient, more nice and smooth.
And how do you see the polygon? Is it a graphics or normal or what?
You mean you want the input form? You want to, then you copy it and then you do input form.
The first question with a polygon is I want to see the polygon. How do I see it?
Oh, yes, it's still a graphics, right? It's still a graphic primitive. Yep. So if I just do graphics of that polygon, nothing changed. It's just that the typeset changed to make it more convenient, more nice. Right? So you can still just copy and paste, manipulate it as a normal expression in the system. Okay, so that kind of make the whole thing quite usable, especially that in 12, we actually enhanced Polygon, added support of Polygon with holes, and a lot of operation. So for example, we have polygon decomposition where you can take a polygon, decompose it in convex, sample, and such, right? And in those cases, you can get, 20,000 polygon after a decomposition. So you want it to typeset nicely in your notebook. So that's why we did all that change, right? Okay, but let's slightly look at polygon with holes. So this case is just a nice example of South Africa and Lesotho, right? Before, to actually do this, you have to use a graphic complex, field curve, right? And define that and have it filled. So now you can just use polygon and define an outer boundary and inner boundary. Right? So our key idea is that any polygon have an outer boundary and a set of inner boundaries, right? So when you describe a polygon, we try to take it, we canonicalize it to that form, right? Even if it's not, and we do the operation. As you can imagine, even if the polygon have a holes, right? If you want to compute the area, if you have the outer boundary and inner boundary, you compute the area of the whole polygon and then subtract the area of the inner part. So that's actually even efficient in terms of computations. Okay. So that's roughly polygon with holes, so I will not dig too much in that. So we also added a set of constructor because actually, I will not say that the definition of polygon is ambiguous, but there is a lot of definition of polygon, especially when they intersect. I mean, when there is no self-intersection of the boundary. Actually, let me start clearly. When you have a polygon, you describe it with the boundary, essentially. So when there is no intersection, well, everything is fine. Everybody assumes that your polygon is described by the set inside the boundary, right? But when there are self-intersection, it starts to be ambiguous, right? So there are several definitions and several interpretations, right? So like in our case, since we have polygon, I don't remember when, since the beginning of Mathematica, we use ray tracing essentially where we define our polygon. So you pick a point, you define a ray, and then you look at the number of intersections with the boundary. If it's odd or even, you define when when your point is inside the polygon or not. So that's one definition, and there are several other ones. So what we introduce in the system is crossing polygon and winding polygon to give you all those possibility to pick whatever definition you want based on the winding number, crossing count on the boundary and such. So that's the key idea of having those constructors in the system. And that kind of roughly give us, in any system, whatever you bring it and whatever the polygon they have, you can just bring it in Mathematica and just apply one of those. Yes, please.
So this is created from scratch. Now let's say I bring in a mesh data from an STL file and then extract the region from that mesh region. Will that also be a similar polygon?
No, so when you import a STL file, by default we generate a mesh object because there the polygon are defined, and usually with an STL file you always assume that is a polygon soup. You describe your object. So there is no ambiguity, right? Usually it's a 3D object. You have a set of things inside. It's for the ray intersections.
Why does it have two properties, the mesh region and the region?
Oh, you mean the importer?
Yes.
Oh, why? Oh, okay, so that's it. So for import, we have essentially a set of property or attribute you pick, right? We have boundary mesh, mesh region, and regions. So if you ask a mesh region, we return you a mesh region object. If you ask a region, we return you a mesh region object with the region wrapper around it. As I pointed out at the beginning, it also will affect later on the type of operation you are doing. Right? So if you are doing a region difference, on the mesh region, we will return you a mesh region, right? But if you are doing a region difference on the region object, that's completely different because we assume that we preserve that fact that mathematically you don't have that, additional boundary which is removed during the difference. So we provide those different attributes just to give you the possibility to build your object the way you want. Okay, so these are the kind of the base constructor which allow us to essentially cover all the possible definition of polygon and you get everything. The other constructor we added is polyhedron. So you can generate a polyhedron, our usual Sparky, and use it as a graphic object or a geometric object. And you can compute the volume and all the standard operation on it. And also what we did is that we added, the basic standard platonic solid, right? So tetrahedron, cube, octahedron, dodecahedron, and icosahedron. So you can just manipulate them directly and they just work, right? And as I pointed before, if you do an input form of also the polyhedron, essentially it have that graphic complex-like syntax where you have the list of coordinates there, and then the list of indices. And generally, we have that form of, rows, outer, inner. Right? Describe the outer boundary and the inner boundary. And that's kind of a canonical form for all our polygons. Okay, so that was kind of what we have in 12. And if you have 12, you probably already have all that. So let's talk about what's coming in the next future version, version 12.1. So one of the first things we did is, to provide you more geometry and enhance what you already have. So we are improving the import and export, faster, better support of, texture, normals, and everything. So kind of the state of the art on that side. So STL will be much better, faster, and such. But also what we are adding is, additional way to actually be able to bring geometry to the system without actually doing the modeling and constructing. So one of the coming functions will be web geometry search. So essentially, you can type a string similar to web audio search, and we try to kind of get you the geometry. In this case, we are returning a resource object, and if you do a resource data on it, you actually get the geometry. Right? And in this case, I believe it's using our resource repository for that, our Wolfram data repository in this case, but we have other external source where we can get those. Actually, let me just show an example. I can actually just do a cow. Hopefully my internet is working. So you'll go behind, use those different resources and give you a set of choices. So in this case, we generate a gallery-like interface, kind of a gallery picker. You can actually look at it and say, well, I want this cow. You copy it, you paste, and you do a resource data. And essentially, then we go and try to actually import that geometry, whatever file format it is, convert it, and return it in the system. So probably the download is taking some time there. So, there you go. So you have the object there. And you can also use the tool and actually see additional information about it. Right? So it's about actually 1 million of edge, more than 1 million of faces and such. And our graphic actually handled it correctly. So that's kind of one way to actually get geometry if you want to play with it. Okay, so I will not talk about this. This is mesh connectivity graph. I think the previous speaker, Jan, already presented it. But the key idea is to give bridge to different areas, right? We already built a bridge. You can use region image to go and get an image. You take a region, you convert it to an image. That's one way. And you can use image mesh to come back, right? And this is another way where you can actually take, a mesh, generate the topology in graph, and apply operation there, and well, we don't have the right, the stuff back, but it kind of disallow you to, do all the nice connectivity analysis and topological analysis on your mesh. So Jan already presented it earlier, so I will pass on that. The other thing we added is essentially topological search, which is similar to the connectivity, right? So if you have, like in this case, a Voronoi mesh, which is a standard question people have been asking, how can you find adjacent cell, which is also kind of similar to the mesh connectivity. So we introduced adjacent mesh cell function. And in this case, I take this cell, which is 2, 1, as I highlighted in red, and you can ask all the cell of dimension 2 which are adjacent to that one, and you have it actually highlighted there. So you can do that for any dimension, 0, 1, 2, 3. And they all work on mesh, right? And they will also work on polygon and polyhedron. As I told you earlier, in terms of usability, we make sure that all of those work naturally. So for those linear primitive, point, line, polygon, and polyhedron, we look at them as those fundamental cells on your mesh object. Right? So it's kind of canonical, and then everything just works instead of adding more additional function for those. Okay. So related to the topological search, we also added the function nearest mesh cell, which is more a geometric search. So in this case, if I still have a Voronoi mesh and I want to find the nearest cell to it, I can just put it there with the nearest mesh cell, and it will give you the indices of those cells. And you can actually highlight it. So, and in this case, it's a more interesting example where you can, hopefully it actually works. Oh, my notebook style is different. Right. Well, in principle, it's supposed to actually highlight and show you the nearest cell as you move the bar. So when the cell here, the highlighting is changed completely. Okay. Well, with the short time I have, I just want to point out 2 main directions we have been going with geometry. So in this release, we are supporting GeoGrid position. So essentially, you can look at it as doing geometry on your chart, on your projected object on the card. So roughly speaking, it's cartographic, so we can do operation on them. So in this case, you can take the polygon of the United States. So you get a polygon of GeoGrid position, and you can actually do computation on it. You can compute the area, and you can actually find the centroid. There we return a GeoGrid position object. And you can actually do the inverse and go back and get the actual geo position. So this is, if you think about it, it's kind of the projected 3D object on the, on the chart, on the card. So we also extended to the same. You can actually do the operation on the globe, on the ellipsoid reference we have for our geographic objects. So in this case, I find the polygon of the US, and now I have a geo position. So there's no projection applied in this case. You can compute the area, which is actually quite similar or close to the geo area. Right? And you can also do the computation on the, on that same object, so centroid and such. So we actually do that on that reference system. And that works with geoposition XYZ, and geoposition NU, such. Okay. Well, thank you. I will just invite you to go to our next talk. Will be advancing number theory, and we have downstairs in the low level demo for AR and VR. Thank you.